test to be on the Tuesday of next week. It's unlikely that I will see you. Well, I'm not seeing you Thursday, Friday. We might have a lesson Wednesday. If you are not present for the test, I will have to chase you down and have you either sit the test before school or on the Wednesday's lesson. Yes? Yes, but I believe the exam periods do not clash.
Yeah, we just got on.
Okay. So, well, here's the option. Either it's Monday and I chase the absent kids on the Tuesday, or we do it Tuesday and I'll still have to chase you. So, science does not have an exam because of the trimesterization of science. So, basically, you treat this as your science exam. Please be present on Tuesday. Okay, if you cannot make it for any reason, I'm happy to do it after school, before school. Hell, I'm happy for you to come in during your exam period and sit it for a 50-minute period, but it has to be done, okay? That being said, I remember I told you about 80% of the test has been made. A further 20% of the test is going to come from this booklet, okay? So there might be, if we cover a few equations or a few calculations in this booklet, there might be some questions like that appearing in the test.
I'm just trying to get into the physics department.
That's okay. You made it. All right. Now, we looked at the little applet yesterday. Now, it shows an inverse proportionality between the temperature and the wavelength. Okay? Now, it's literally the inverse. So if you were to double the absolute temperature, then the average or the maximum wavelength would be half. And we see that through observation that hot objects will glow red, then they will glow orange, then they will glow white. Very quickly to remind you, if we go back to the applet, starting at a light bulb down here which might glow orange. Now you cannot really see it, but again, it is emitting all of those. A lot of infrared, a little bit of red, a little less orange, a little less yellow. And as it gets hotter and hotter and hotter, obviously the intensity increases and the wavelength gets smaller. Okay? And what we got to yesterday is I pointed it at a light bulb. And that is what we detected. So the spectrometer, this was the light being emitted. Okay? We've got short wavelength down here, long wavelength down here. Now it goes from 350 through to 900, which 350, that's just beyond ultraviolet, and 900 is just beyond infrared. As we recall from your poster, our visible light is around about 400, 380 up to 750. Okay, so this distribution, this is called a continuous emission. Yes. B, we'll discuss that. We will discuss that in just a moment. Hold on, because I said something incorrect. This is called, and we will label it in a minute. This is a continuous spectrum. This isn't by the way. I know, which is why I want you to pay attention, and I'd like you to stop talking. Now, it gave us the maximum or the peak. So again, don't think maximum as being the largest. The maximum is the most frequent. The most relative intensity was that 629 nanometers. So this equation, if we just have a look at it, that's just a constant that relates temperature to wavelength, and it was determined by some bloke called Wein. We can figure out its temperature. So if I was to rearrange temperature, that's going to be B divided by lambda. And we can simply take that 2.898 by 10 to the negative 3, divide it by our 629 nanometers, and that should give us the temperature of the filament. Now, I'll need somebody to solve that in their calculator, please. Sorry? You want to, what?
Don't worry, sir.
All right. You shouldn't be talking anyway without raising your hand.
So is that
629 nanometers. So 629 nanometers.
In 3 sig fig, 4 fat 4,610.
And it's in Kelvin. If we wanted to get it into degrees Celsius, we would have to subtract 273.14999. Yes?
So B is constant.
B is just simply a constant. There it is there. That's the constant there. And now it has the unit. The question was asked, what are the units? We could rearrange for B. That's just going to be lambda times T. So it has the units of meters Kelvin. Now we put a little dot there so as not to confuse you that it's not millikelvin. Okay? It's not Kelvin times 10 to the negative 3. It's meters Kelvin. It's, again, not a very useful unit for us. It's a constant of proportionality. It puts units of Kelvin into wavelength and wavelength into Kelvin if you have one or the other. Now the cool thing about this, if we have the time and if it doesn't appear too overcast, we can take this spectrometer outside, point it at the sun, and we can get the continuous spectra of the sun, or at least the surface of the sun. We will get a very similar shape as that, or as that. And by measuring the peak wavelength, we can figure out what the surface temperature of the sun is. Okay? And it comes out to be about 5,600 Kelvin. Come in here. Oh, is that light flickering again? Oh, sorry. I will get that repaired. There's like 800 of these fluoro tubes in physics, and they always die. Sorry, Tristan. So, shush. One other cool application to this is that you can take an image of any object above 0 Kelvin, and you are going to get from certain regions in this picture, you are getting certain wavelengths, maximum wavelengths corresponding to a surface temperature. So, for example, we could see that this region of this image has a shorter wavelength, therefore a higher temperature. This region here at the top of the image has a longer wavelength, hence a lower temperature. And so you can get these special cameras, and the science department has purchased a FLIR camera, and it's looking at all the different wavelengths coming from all the different regions in its view. Thank you. And it's putting it to a contrast image. And so all you need to do is take a picture, and it then tells you what the surface temperature of the object is. Okay? So that is a FLIR camera. If we said we had a surface temperature of 32 degrees, that's about 300 Kelvin, you could figure out the wavelength emitted, and it comes out that it's being emitted in infrared. So you are all emitting infrared. Your surface is not hot enough to be emitting visible light. In order to emit visible light, you have to be up at around about 1,000 Kelvin, and then you will start to emit red photons of electromagnetic radiation. At the moment, you are not hot enough, so you are only emitting infrared. Okay? If you are lucky, and while you're going around, I'll go get the infrared camera, take a picture of the class, and we can have a look at the thermal image of the classroom. Precisely. So that was Wein's law. Very, very simple. Over the page, gentlemen. I'm sort of teaching you all of these little snippets because eventually we're going to bring it all together and explain how Hubble came to his model. Why are you talking? Shush. Great. Do you want to go and sit with the Year 7s in Year 7 science? Then act like a Year 10 student, please. We're going to bring all of this together to properly understand how Hubble came to his conclusion about the state of the universe and how we became to be. Now, there was an issue that plagued early astronomers. There's two types of brightness. There's an intrinsic brightness, which is the amount of light intensity that the object actually emits. For example, a 40-watt globe emits 40 watts of power. And then there's the apparent brightness. The apparent brightness is what we can observe. Now, if I took that 40-watt globe and placed it a metre away from me, I would measure an apparent brightness. If I then placed it twice the distance, the apparent brightness would be a quarter. Now, what happens, could you just write here, please, intensity is proportional to 1 on r squared. It's an inverse square proportion, which means as you double the distance, you get a quarter of the intensity. If you triple the distance, you get 1 on 3 squared, you would get a ninth of the intensity. So what I want you to imagine is, suppose you are standing out on the oval and it's pitch black. It's middle of the night, there is no light sources, it's just absolutely no light at all, okay? And you see a light, a certain distance, well, no, you don't see a light. You see a light and you measure it to be about 100 watts of intensity, okay? Now, the problem with that is that you don't know how far away that is. What you could also observe is another light that appeared the same brightness, but it could actually be 400 watts, double the distance.
Wait, I'm somewhat confused. Sorry, for apparent brightness, is that the amount of energy that's reaching us, or?
The apparent brightness is the magnitude of the brightness that we measure here, yes. So when we look at the sun, we can measure its apparent brightness. That's how much light actually gets to us.
So if something was 100 watts, then it would probably most likely be like thousands or millions of watts.
Oh yeah. If it's really far away, it would be really bright.
No, even like a meter, if we...
Hold that thought for a moment. If I saw this, now I've just given you the actual intrinsic brightnesses, right? But imagine you're out in pitch black and you see these two lights. If that's the scenario, using the inverse square law, 1 over 2 squared, you would get a quarter of that. You would see them both appearing the same brightness. And you would have no way of telling whether they were both 100 watts a meter away, or it was 100 a meter and 400 2 meters away, or maybe it's even, I'm bad at maths, 10 on 9, 11 watts, sorry, 900 watts that was 3 meters away. We could keep going. It could be 1600 watts that was 4 meters away. You've got no idea. All you can see are 2 equally bright lights. And without knowing this number, which what it could actually be, that number could be written on the side of the torch. Okay? But there's no way to travel to the torch and look at it. You can't look at the power rating on the side of the star because we can't travel to the star and peer inside and see what's going on. So that was the issue that plagued the early astronomers. What was needed was a standard candle. We put that in apostrophes, quotation marks. If you could look at a star and go, oh, I know that type of star. It's got an intrinsic brightness of this. We then measure the apparent brightness, and then by knowing the two values, you can figure how far away it is. So that's my example. If I said, aha, I know that it's actually a 400 watt candle, and I'm measuring it with a brightness of 100, and using my inverse square law, I could say, I know that it's 2 meters away, and not 1, and not 3, and not 4, but 2. Okay? Yes, J-Bob.
So say you're in the vacuum space in a very, in an area that isn't populated by a lot of matter, and you're floating somewhere you can survive, would you be able to see yourself?
If there's light.
Would light be, say, right, this is confusing.
All right.
Light doesn't...
You can email me anytime after hours and I will respond. Joseph, we don't have much time left. Talk to me after school. He was fortunate. There was another astronomer, a female astronomer whose name I forget all the names. They discovered a relationship. There was a certain type of star called a Cepheid variable, and it pulsed in its intensity. So it went from bright to dark with a constant period of pulsing. And better yet, that the period of the pulse was directly proportional to its intrinsic brightness. So all you had to do was find one of these types of stars that was pulsing and just measure its period of pulse. And sometimes it ranged from a period of hours through to days. And the longer the period, the brighter the brightness, okay, or the intrinsic, I should say. That's all you needed to do. In fact, look at the screen, please. At the start, there was data, all right? And they knew that there were Cepheid variables, and they had data like this. And you'd look at that and go, well, there's not much of a correlation there. That's your Cepheid variable. More investigation in astronomy revealed that there were actually two types of Cepheid variables. Cepheid variable 1, Cepheid variable 2. And obviously, once they had that, they go, look, we've got even more data to collect from. And both the 2 and the 1s had their own little correlation coefficients. Okay? So, all they needed to do was find these distance markers. They simply found a Cepheid variable, measured its pulsing, and then they could go, all right, I know that star is so many thousand parsecs away, for example. Okay? Happy so far? So this is one bit of data that he used. The Cepheid variable enabled him to figure out how far away the star was. Before we jump into what else Hubble used, we need to look at different types of spectra. So, turn over the page. We are going to spend the rest of this lesson looking at different types of spectra that an object can emit. As we said, blackbody radiation is the emission of electromagnetic radiation of any object above 0 Kelvin. You are all emitting it now. The incandescent globes, any hot object will emit a continuous spectrum. What I want you to imagine is that the hot objects contain particles which are jiggling. And the hotter they are, the faster they're jiggling. They're all containing charges, protons and electrons. And so now what you have is moving charge. And if you take a charge and you wiggle it, you make these ripples in the electromagnetic medium. We call them EMR or EM waves. If you jiggle faster, you emit shorter wavelengths, higher frequency. Now there's so much stuff going on inside a hot object that you've pretty much got every possible variation of jiggle and hence every possible variation of wavelength being produced. And so if you were to observe through a spectroscope, you're not going to see a discrete line, but you would see a continuous curve being capped out at a maximum that correlates to, well, we can't make it jiggle any faster. And then obviously at a minimum would be the slower jiggles. So a hot object is obviously going to be making radio waves, but it's also going to be making ultraviolet and possibly gamma rays if it's a really, really hot star. If it's our star, that's what it's making. So again, as I said, if I went outside and pointed my spectroscope, we would get this continuous spectrum. It would have a maximum in around about the green region, and Wein's law would tell us that its surface temperature is 5,800 Kelvin. We also know that it's emitting some ultraviolet, but the atmosphere blocks it out for us. Yay. Okay? So, all hot objects emit a continuous spectrum. Next, you can get discrete wavelengths if you cause an object to be excited. If you ionize it or if you pass electricity through it, you can cause your atoms to be excited. Now, what's going to happen, and I don't know why I've got this blank space down here, the emission spectra, what I would like you to imagine, here is an atom with electrons in fixed orbitals. And I hope that your extension chemistry has taught you that if an electron is excited up, it needs a certain amount of energy. And if it was to make a transition from an excited energy level down to the ground state, or in fact to any state, it's going to emit a photon of light. And so you could have electrons, if there is a vacancy, they can fall down, and in doing so, they emit a photon. And in fact, we could have an electron could even do that. So I've just drawn there were three possible transitions. We could go from the ground state, n equals 2, n equals 3, I've got n equals 1, I've got 3 different energy levels. And essentially, if you excite the heck out of something, all of the electrons get bumped up, and when they make the transition back down, they emit a quanta, a discrete, that's the key word, a discrete photon of light with its own energy, its own frequency, and its own wavelength. So for example, I don't know what this is. This is water vapor. Water vapor H2O. And so it has certain energy levels. And when the electron, basically we've got electrons whizzing through the water vapor, there's 4,000 volts of electrical potential, so you've got current flowing through. Our electrons are being excited, and when they fall back down, they emit a certain wavelength. Now, that looks to us like a colour, and looks purple. However, what we're going to do in just a moment is you're going to view this with a spectrometer, and you will see that it's not just purple, it might be a few different discrete wavelengths of light. Okay? And even better, each element has its own energy levels for its electrons, and so it has its own discrete emission spectra, just like a barcode. So water vapor appeared purple. What the hell is this? Helium might appear slightly yellow and orange. Okay? And all we need to do is measure the wavelengths, and we can identify the elements. Okay? If we turn the page, you don't have to learn about this until year 12 physics. That's my horrible, terrible diagram. Turn over the page. So, as I said, hot objects produce a continuous spectrum. Okay? If you, again, we will get you in just a moment to observe a hot object. I believe we have a couple of hot objects here. Yeah, a little peep show going on there. Point through, you can look at the hot light, and you would see not a discrete wavelength, but a whole smudge of visible light. You are seeing every single possible visible light photon being emitted. Okay? Then, if we were to hot gas, could you also write /ionized? And you pass that light through a diffraction grating and split it up, you would see a discrete wavelength, a red wavelength, an orange, a couple of green, a couple of blue. Again, it's unique to each element. Okay? Now, it has been discovered. Yes, Matthew Darling?
Yeah, so when you say a hot object, does that just mean above 0 Kelvin?
A hot object
Like it's emitting its own?
basically needs to be a plasma. So what we're talking is the sun. Inside the sun, you've got hang on, no, bad example. Hot gas. It needs to be so hot that it is jiggling so much that electrons are being pushed off it. It's being ionized. So yeah, we're literally talking plasma.
So, well, if humans don't emit a continuous spectrum,
We do emit a continuous spectrum.
so are we a hot object then?
Yeah, anything above absolute zero.
Yeah, that's
Oh, okay, I get you. No, yeah, we're emitting this. We are not a plasma, nor are we ionized. So we emit this,
Yeah.
emitting infrared. All right. Now the next thing. This was it's called the Bohr model of the atom, which wasn't really introduced until 1905. This explained emission spectra, but it also explained absorption. The opposite can occur. If you have a cold gas and you pass white light through a cold gas, meaning all of the electrons are down in their ground state, they're not excited, those electrons can grab certain wavelengths and promote them up to higher levels. And then when that white light passes through the gas, certain wavelengths will be missing. Okay? And then only those wavelengths will be detected. So if we were to pass white light through a cold gas, you can see that wavelength's missing, that wavelength's missing, and these were, but they're exactly the same discrete wavelengths. Okay, so it's like the inverse of a barcode. If I gave you a barcode and you inverted it, and you had the inverse, well, you'd be able to pretty much tell that they were the same barcode, right? Yes?
By cold gas, you mean 0 Kelvin?
No, so cold gas means at a temperature where all of the electrons are in their ground state. When you thermally excite a gas, through all the motion and jiggling, electrons can be promoted up to higher energy levels. And then they will start to emit a spectrum rather than absorb. Okay?
Would normal air have an absorption spectrum?
Well, air is made up of various
Okay,
gases.
would say like pure, I don't know, wait, I don't know, argon? Does
Yes.
argon have an absorption spectrum?
Yes. We don't have an absorption spectrum set up. You can get a solution of potassium permanganate, and you put a lamp behind it and a purple solution in front, and you look at your spectroscope and you would see missing bands. Okay? So you would see this kind of scenario.
So does it have to be a gas then? Does it have to be a gas?
Nope, it can be a solution. It can be a liquid. Again, here's hydrogen. So again, if you excite hydrogen, now we have hydrogen set up somewhere around. When we turn the lights off and you look with your spectrometers, you will see hydrogen. It glows purple, okay? But it's not actually purple. It is 1, 2, 3, 4, 5 different discrete wavelengths. The majority of them are on the blue end, but there's also a really dark red band. So even though a red photon is bombarding your eyeballs, these guys kind of win out. And so your brain is taking all of these photons in, and it's going, oh, it looks purple. So your brain interprets it as purple. But your spectroscopes are able to differentiate. They split the light into their discrete wavelengths. Yes, Matthew?
So there's photons which are light particle and then there could also be a wave.
Yeah, so I don't want to freak you out yet with the wave particle model of light. We're going to stick with photons as having wave-like properties. So this is a certain wavelength. So for example, gentlemen, remember we said that down this end was 700 nanometers and this end was about 390 nanometers.
Where's 380 and 750?
It varies. Let's go 750. There you go. See that 0 turned into a 5.
And
Again, it varies. Certain some posters will say 390, some will say 400, some will say 380. It does vary. But again, these ones don't measure wavelengths, but the SpectroVis, the digital one, I might point it and we can actually measure the bands of light that are coming out. Okay. So this is what we are going to do for the next 5 to 10 minutes. One between two. You're going to come up and grab these ones in the blue plastic cases. Work the best. Oh, I think these ones are new. Ooh. Bending themselves somehow.
Is it just a cap you need to remove?
Twist it. Oh, we got some new ones. Oh, and they're beautiful. All right, cool. Gentlemen,
Grab it.
there's a tapered side, there's a flat side. The tapered side goes towards your eyeball and the flat side you point towards the light source. We have some incandescent tubes. We have some excited gases. If you would like, just briefly open the curtain and point your spectroscope outside and you should hopefully see a continuous spectrum because the sun is producing that. Okay? Please do that. You might want to inquire as to what your iPads are producing. Come and grab a spectroscope, please. Oh, hang on. Stop. Don't move. Stop. Gentlemen, a couple of things. These black boxes, they are high voltage transformers. Please do not touch the glass. Simply touch the power button on the side. As well, only leave the glass tubes on for about 20 seconds and then turn them off and let them cool back down. If they stay on for 5 or 10 minutes, they can get corroded and damaged, alright? So just remember those two safety warnings. Grab a spectroscope.
Let's try.
No, take a blue one. There is it.